7th grade. So this lesson is 4-4 greatest common factor. We will be talking about this section 4-4, which you can find in your books or on the photos that I sent you on page 164 through 167. You have two vocab words to take care of. So you need to put your heading on a piece of loose leaf and then take care of these two vocab words, Venn diagram and greatest common factor. Go ahead, pause the video and do your heading and vocab. Our vocab words, Venn diagram is one that I'm sure you have seen in English class, but I'm not so sure you have thought about it in math before. So a Venn diagram in math is going to look very much like a Venn diagram in English would look or literature would look. You've probably seen them in science class too. You have two topics that some things are different about them and some things are the same about them. So let's do learning in school and learning at home. So in both, you are learning. In both, you have your teacher. Obviously, home learning, let's see, we don't have the smartboard, which I still miss. You don't have to wear your uniform. You can wear dress down day every day. Dress down day every day. At school, you have desks. Maybe at home, you don't. At school, you have to wear your uniform. And at school, you have more of a schedule you have to keep. So here, we're still doing work. We're still learning. We still have teachers. At home, we don't have, I'm going to put no smartboard. We don't have a smartboard. At school, we have desks, we have uniform, and we have more of a schedule. Greatest common factor is when you have two numbers and you're trying to figure out what is the biggest number that goes into both of those numbers without a remainder. So when you are given two numbers, say we're going to look at 12 and 20. When you're finding that greatest common factor, you're looking for what number goes into both of our numbers. So you're always going to start, and please write this in your notes, always start with your biggest number. I'm sorry, that was wrong. Always start with your smallest number. What I mean by that is we're going to look, in this example, we're going to look at 12. 12 is our smallest number, so we're going to start there. Does 12 go into 20 without a remainder? Doesn't. So we need to keep working at this. So if your smaller number does not work, you're going to start thinking about what are my factors of both of these numbers. And just like we did in the last section, you can think about a factor tree. So we can break this down into 2 times 6 and then 2 times 3. We can break 20 down into 4 times 5, 2 times 2. So 12 has a prime factorization of 2 times 2 times 3. And 20 has a prime factorization of 2 times 2 times 5. So now that we know our prime factorizations for both of our numbers, we can go in and we are going to circle anything that is on both lists. So we have 2's on both lists. We also have these 2's on both lists. These don't match something on the other list, so we're going to ignore those. So the things that we have circled are 2 times 2. So what that tells us is that our greatest common factor for 12 and 20 equals 2 times 2, which equals 4. So our GCF for 12 and 20 ends up being 4. Now, you may have been able to do that one without doing the factor trees and figuring out what's on both lists, just by thinking about what are the numbers that go into 12 and 20, and you probably could have come up with 4 as being your greatest common factor. If you can't, though, this is a method that will work every time. If you factor tree, set up your lists, figure out what's on both lists, and then you're going to multiply everything that's on both lists, and it gives you your greatest common factor for your 2 numbers, or your 3 numbers if you have 3. So I'm going to erase this, and I'll be right back with you. We are going to move on to example 2 on page 165 now. Example 2 asks us to, again, find the greatest common factor. This time we're looking at the numbers 30 and 24. So again, I would guess that a lot of you can look at those 2 numbers. You're going to always start with that smaller number. 24 does not go into 30, but I bet a lot of you could think about those 2 numbers and figure out what the biggest number that goes into both of them is. I'm going to show you the factor tree method again so that you can see it in action. So with 30, we have 5 times 6. I really like you to circle those prime numbers when you find them. Here we have 2 times 3, which are both prime. So our prime factorization for 30 is 2 times 3 times 5. Now I'm going to do a factor tree for 24. I could say 4 times 6 is 24. 2 times 2, those are both prime, that equals 4. And here we have 2 times 3, which are both prime, so our factor tree is done. And we can say that 24 equals 2 times 2 times 2 times 3. So now our job is to go in and see what is on both lists. So I'm going to go through and say, well, I have a 2 on both lists. Now I have these 2's as well, but there aren't any more 2's on my prime factorization list for 30, so I don't circle these 2's. I only circle the ones that match exactly. Sorry about that. Sorry. All right, so in looking at my list, I also have these 3's that match. These dry erase markers really stink. All right, so I also have those 3's that match, so those get circled as well. Now, I do not have a 5 on this list, so that's not going to get joined our circles. All right, so we have circled our sets of 2 and 3, and now I just need to multiply everything that is circled. So I'm going to say 2 times 3, which equals 6. And some of you may have known already that our greatest common factor for 30 and 24 equals 6. Looking at the next example, we have 3 numbers on this one. So this time I am going to start out with 54, 36, and 45. Always start with your smallest number. If it goes into your other numbers without a remainder, you're done. This one unfortunately does not. So we need to think about things that go into each of these numbers. So for 54, we can say that 6 times 9 is 54. This breaks down into 2 and 3. And this one is 3 and 3. So 54 equals 2 times 3 times 3 times 3. 36, 6 times 6. So prime factorization for 36 is 2 times 2 times 3 times 3. 45 would be 5 times 9. And I have 3 times 3 times 5. So now that we have our lists, we have to figure out what is everything that is on all 3 lists this time. So I have a 2, but I don't have a 2 in this list, so I don't circle the 2s. Here I have 3, 3, and 3. And then I have another 3, 3, and 3. I only have 5 on this list, so that doesn't count, and this 3 is left alone because I only have 2 3s, 2 3s, and 2 3s. So I end up with 3 times 3 for my GCF of these 3 numbers. 36, 45, and 54 equals 3 times 3, which is 9. So the biggest number that goes into 36, 45, and 54 without any remainders is 9. So that would be your answer here. The next thing that we have are monomials. So example 4 goes back to the monomials that we have talked about previously. Just as a reminder, monomials are numbers and variables that are separated only by multiplication or division. You cannot have an addition or a subtraction sign in a monomial. So monomials are going to be things like 16xy squared and 30xy. So problem 4 gives us these 2 monomials, and we are supposed to find out what is a greatest common factor for those 2 monomials. Now, in the last section 4-3, we factored monomials already, so you should feel pretty comfortable coming in and saying that the prime factorization for this variable would be 2 times 2 times 2 times 2 times x times y times y. For 30, you would have 2 times 3 times 5 times x times y. So now that we have the prime factorization for these, we can come in and say, okay, well, I have a 2 on both lists. That's it for my numbers. I don't have any 3s over here. I don't have any 5s over here. So our number is just going to be 2. And then I have an x on both lists, and I have one y on both lists. So my greatest common factor between 16xy squared and 30xy is going to be 2xy. Now, some of you may have been able to look at these two numbers, and if you think it through and you think, okay, I have 16, I have 30, what's the biggest number that can go into both of those numbers without a remainder? You may have been able to come up with that too in your head. If that's the case, that is perfectly fine. You would just need to write this for your answer. Okay, don't forget your variables are there, and you need to be picking out what variables are on both lists as well. The trick, if you're writing these with exponents, let me show you what you do in that case. So say we had our 16xy squared and our 30xy, and we wrote the prime factorization using exponents. So there I have to think about, well, how many 2's do I have? I have 4, so I do 2 to the power of 4. I have 1x and I have 2 y's. And then with 30xy, I would have no exponents actually. I just have 2 times 3 times 5 times x times y. When you are using exponents, what you're going to do is use each number that is on both lists and use the lower of your exponents. So even though none of these have exponents on them, what that means is our exponent is understood to be 1. So you would look at your list, see that you have 2 on both lists. So you use a 2, you use your lower exponent. So we have a 4, we have a 1, our lower exponent is 1. Then we only have 3 on this list, so we can ignore the 3, we can ignore the 5 because it's only on this list. Our our x's are on both lists, both exponents are 1. Our y's we have on both lists, this exponent is 1, this exponent is 2. So the lower of the exponents would be 1, and you can tell that we got the same answer because if, again, there are no exponents, it's understood to be 1. So those are mathematically equivalent. We got them in the same way. If you are using exponents, just remember the base has to be on both lists, and you would use the smaller of the two exponents. The final example in the section is example 5. And for example 5, I need you to remember back to when we did the distributive property. So when we did the distributive property, we had things like this. 2, and then in parentheses, which means times, x plus 3. When we distribute, we have to take our coefficient, the number outside of our parentheses, times each of the terms inside the parentheses. So we would do 2 times x, which is 2x, plus 2 times 3, which would be 6. So this is the distributive property. What we are looking to do in this section for 4 is to take something like this expression, and we're actually going to do the opposite of the distributive property. So to do that, you have to figure out what is the greatest common factor between these two terms. So we are going to think about 2x and 6 separately, and we're going to figure out what is our greatest common factor. Well, we don't have an x in both terms, so we know the variable is out. We have coefficients or constants of 2 and 6. The greatest common factor, the biggest number that goes into those, you're always going to think of your smaller number, 2 in this case. It does go into 6 without a remainder, so your greatest common factor here is 2. What you do is pull your greatest common factor out. So we're pulling it out of that term, and we're also pulling it out of this term. So 2x divided by 2, 2x divided by 2 would just be x. You bring down whatever your operation is. Then you also have to do 6 divided by 2, which would be 3. Notice we came up with what we started out with before we distributed. That's showing you that the distributive property and factoring out of your terms, factoring and expression are opposites. It's just like addition and subtraction are opposite operations. Distributing and factoring are also opposites. Let me show you another example of this. So if we had 3x plus 9, and we're going to factor this, we have to think about what is our greatest common factor of 3x and 9. Again, you only have this one variable. There's no variable over here that matches. So we don't need to think about our variables at all. We're just thinking about our numbers. You start with your smaller number. Does 3 go into 9 without a remainder? Yeah, it does. So that is our greatest common factor. Once you've figured that out, you can go ahead and bring that operation down. Now you need to divide each of these terms by your greatest common factor, which was 3. So we're taking 3x divided by 3, which just leaves x, and 9 divided by 3 is 3. So we have our factorized expression here, 3 times x plus 3. If you would reverse this and do the distributive property, we should end up with this. So that would be a good way to check these. If we distribute this 3, remember you have to distribute it to both of your terms. We're going to take 3 times x, bring our operation down, and then 3 times 3 is 9. Notice that matches what we started with. That is actually the last example that there was for this section. I am going to go ahead and give you some problems to try. So you're going to try these, and I really want you to watch this video and try the problems and then snap a picture of the problems and send that picture to me. Either submit it on Reddit or have your parents email me the picture of your work. And I would like that turned in by tomorrow, which is Wednesday, by noon. That way, after noon tomorrow, I'll post another video where I go over that homework. And if you turned it in before noon, you will get credit for that as having your homework turned in. And I'll go ahead and post the video of me going over those so that you can see some more of these problems solved.